The functions that arise naturally in most mathematical applications are typically continuous. Polynomials, trigonometric functions, exponentials, logarithms, these are the types of functions we have in mind. Now you'll say, well, hang on, not every trig function is continuous. What about the tangent or the cotangent or what have you? Yeah, you're right. Continuous over some intervals, and the same applies for rational functions and algebraic functions. Intuitively, we say that a function is continuous at a point if it is possible for us to trace the graph of the function through that point without having to lift our writing utensil. But that is an intuitive notion. It is not a formal definition. And the notion of continuity is actually super important in calculus and in analysis. If you ever take topology courses, you'll see that we can define continuity in a different way as well. It doesn't rely on the notion of a distance, but which relies mostly on notions of openness sets. So let A be a subset of the real numbers, let F be a function from A to R, and C be some point in A. And here, note that we're not saying that C is part of the closure of A. We're not saying that C is a limit point of A. We're saying that C is a point of A itself. F is continuous at x equals C if the limit when x goes to C of the function f at x at C. And you see why it's important that C belong to A if C belongs to the closure of A. C is a limit point which is not actually in A. F at C would not be defined because the domain of the function f here. Now what does that mean from a epsilon delta point of view? If for every epsilon greater than 0 you can find a delta epsilon greater than 0 such that difference between f at x and f at c can be made as small as possible, smaller than epsilon, whenever x is in A and x minus c smaller than delta epsilon. And here, because we might actually allow x to be equal to c, we do not have the typical strictly greater than 0. See, the definition I gave you here is only valid if C is actually a limit point for set A. Now we've seen examples where C is a member of A, but C is not a limit. In fact, this here is the true general definition of continuity at x equals C, and this is the definition if it turns out that C is a limit point of A. There are three statements in this case here. First of all, you are showing or saying, first thing you're saying is that f at C is defined. It wouldn't be too much of a surprise given that A is the domain of the function and C is in A. Then we're saying that the limit when x goes to C of the function exists. And finally, we're saying that this limit is actually exactly the same as the value of the function. When you compute the limit, in general, you're interested in values of x near C, but not equal to C. When you're talking about continuity, you're also interested in the value of the function at that specific point. Now, if C is not a limit point of A, then the expression limit of the function when x goes to C does not make sense. Right? Because you have no sequence xn in A and not equal to C for every n such that we compare this to C. When that's the case, we just say automatically that f is continuous at C. If you let B be some subset of A, f is continuous at every C in B, and we'll say f is continuous on B. Let's look at some examples. If f be the function from 0 to R, we've seen it before, it's defined either as 2 or 3, depending on the value of x. So if it's between 0 and 1 strictly, it's 2. And if x is equal to 0, the value of the function is 2. And we know that 0, the limit point of the set 0, 1. The point 0 is in the closure, 0, 1. So the only thing we need to verify in this case is the limit when x goes to 0 at x into f at 0. We've already seen that the limit when x goes to 0 of f at x is 2. We know what the value of the function is at 0. That's equal to 3. 2 is not equal to 3, so f is not continuous. 0. Let's revisit the function which assigns to each non-negative number the following quantity. I feel like we've seen this function before. If we haven't seen this specific function, we saw a function quite like it. Is it continuous? It's equal to. Well, 2 is a limit point, this set, so it's enough for us. The limit when x goes to 2, x squared plus 2x plus 2 divided by x plus 1 is the same as 2 squared plus 2 times 2 plus 2 divided by 2 plus 1. We've already seen that this limit is 10 over 3, one of the preceding videos. 2 squared plus 2 times 2 plus 2 divided by 2 plus 1. This gives me 10 over 3. These two things are equal. So this function f is continuous, c equals 2. And remember, we computed, or we showed that the limit was 10 over 3 using the epsilon delta definition, or potentially the theorem that allowed us to make the link between computing the limit and finding sequences. Well, what about these other ones? What do you think about this? Is it continuous or not? I'll let you try to figure it out. Same for this one. You might be wondering why I'm not just calling this x minus 1. What I'm trying to describe here is a function which would be the function x minus 1, except that 2, there would be a hole. Right? So this is the quickest way you want of writing this using only one expression. If I do the cancellation, this hole here would be filled, and that's not. Is it continuous? C equals 2. It can't be, because the function is not defined at c equals 2. If at 2 does not exist, the function cannot be continuous. Or do we say, well, hang on, your choice of r is not the right choice. This function cannot be well defined. Instead, define it on some other domain. Now, the function does not exist. C equals 2 is a limit point of the set to infinity, but C does not belong to infinity, and we've said there that automatically the function is continuous. What do you think is happening here? Is the function continuous or not? What about this function? Takes on the value 0 for rational values, takes on the value 1 for irrational values. The function continuous, c equals 0. Now we've already seen that the limit when x goes to 0, which is a limit point of r, does not exist. This limit does not exist. It, amongst other things, cannot be equal to f at 0, which would be 0. So, no, not continuous. X equals c. Now, slightly different function from r to r, which takes on the value x if x is rational, and 0 if x is not rational. Is f continuous at c equals 0? Not the same function, the one we had here. Different function at c. Well, we know that f at 0 is 0 in that case. So we need to show the limit when x goes to 0 at x is equal to 0. The only natural approach to use here would be the definition. Let epsilon be some positive number, set delta epsilon to be exactly epsilon, also a positive number, then the difference between f at x and f at 0, f at x minus 0 is going to be equal to, well, it's going to be equal to f at x. And by construction, f at x is either x or 0, which means that it has to be smaller than or equal to the norm of. If it's equal to x, then absolute value of f at x is exactly equal to the absolute value of x. And if it's equal to 0, then 0 is smaller than or equal to the absolute value of x for every x, including 0. That sort of makes sense. Now this absolute value of x, I can rewrite it as the absolute value of x minus 0. And then I'm assuming that this is less than delta epsilon whenever, of course, x minus 0 is smaller than delta epsilon, and x belongs to the domain A, which in this case was R. So all good. And delta epsilon said was equal to epsilon. And what I found here is that for any epsilon greater than 0, I can show you that the difference between the value of the function and 0 is going to be less than epsilon whenever x is close enough to the limit point 0, whenever that is smaller than delta epsilon. And so the limit when x goes to 0, this function f at x is equal to f at 0. F is continuous at 0. It's continuous at 0, this function, but that's the only point where it's continuous. At any other point, the function is not continuous. Now we will prove this. Look, pick some integer. We have a density theorem about rational numbers that tells us that there exists a rational number xn and an irrational number yn, which are such that xn is squeezed by c and c plus 1 over n, right? There's at least one rational number between c and c plus 1 over n, and yn is squeezed by c and c plus 1 over n. Now, by the squeeze theorem, all of my sequences here go to c, and so my xn also goes to c, and my yn goes to c. They have been picked specifically so that xn and yn would never be equal to c, but that's not important when we talk about continuity, right? This is because here of the density result. Now what we do know is that f at xn is going to be equal to xn because xn is rational. We also know that f of yn will be equal to 0 if yn is not rational. So it's true for every n. Well, what's the limit of the xn's then? C. So the limit of f at xn is c, because we found here that the xn's go to c, and the limit of f at yn will be the limit when n goes to infinity of 0, which is 0. So I have here two sequences. They both go to c, and the corresponding sequences of function values, f at xn and f at yn, go to c and 0, which are different. We found two sequences converging to the same c, or for which f at xn and f at yn go to different value. This means that the limit does not exist. And if the limit does not exist, in particular, it cannot be equal to the value of the function at c. Conclusion here, write it in a different color, f is not continuous at c, which is different from 0. End of